Welcome to the 8th and potentially final episode in our Antenna Brief series. We're going to cap off the Antenna Brief series with an episode on designing antennas. And because this is such a big subject, as in some of the other videos, this is going to be in two parts. So what you're seeing here is going to be part 1, which is going to cover the essentials. As you may know, if you've seen some of our other videos, this material is based on and designed to support a university course. However, I'm hoping it works for individual learning as well. Now, what we're looking at here is a 2-page class handout that I gave in a couple of the different courses where we touched on antennas. Let's take a quick peek at this. Here you can see some of the main antenna types. Of course, there's the half-wave dipole antenna, and something called a folded dipole that is very similar. It just has a different input impedance. And then, of course, the monopole antenna that we showed on the cover slide, and a short monopole, something that's not lambda over 4. And we'll touch on what happens when you do that. And it kind of hints at it here. And loaded monopoles and so forth. Now, I'm not going to go over this slide right now. We're going to come back to this later in this video. But I did want to show you, in case you're curious now, some of the different types that we're going to talk about. So before we go into all these different antenna types, we need to cover a little bit of background. And here's how we're going to do that. This is our topic list. We're going to start right off with how to design an antenna. And as an engineering person, that means understanding the requirements for the design. Then we'll look at how you can make a very quick and simple antenna. And as we'll see, it doesn't take much to do that. And that's both good and bad. It's bad because in some situations you don't want to have an antenna. So a lot of electronic products, especially these days with switch mode power supplies and so forth, can put out a lot of radio frequency noise. And so we'll touch on how to not make an antenna. And that will, of course, complement and inform how to actually make an intended antenna. And these first 3 bullets are what we'll cover in this part 1. In part 2, we'll go back to that overview slide that I just showed you with the class handout and look at common antenna designs. And we'll show some examples, some pictures of those. And finish off with how you could design your own antenna. Some research projects we've had have called for special antennas, and with the student team, we designed and built them, and we'll take a look at them at the end of part 2. So back to design requirements. What does the antenna need to do? Well, you need to know the frequency or frequency range, and you may have a size constraint on your antenna. However, as you may know if you've watched the first episode in this series, frequency and size go together. We need to be on the order of half a wavelength, a quarter wavelength, maybe a tenth of a wavelength to make a good, efficient antenna. Now, it also matters what the use of the antenna is going to be. If it's a transmit antenna, then what I just said is true. I mean, you just can't make antennas too small relative to the wavelength. However, for receive applications, it might be okay to have an antenna which is not just great. And of course, transceive means you're transmitting and receiving, so same requirements as a transmit antenna. And in that case, the impedance of the antenna is very important. You want to get all the power that you're creating in your electronic transmitter out the antenna. And directivity matters because it's highly linked to gain, as we've seen in some previous episodes where we talked about propagation and signal strength at the receiver. And also the pattern, which is, again, directivity. And we haven't talked too much about it yet, but we did demonstrate briefly the effects of polarization. It's important to match the polarization of the transmit and receive antennas to some degree. And finally, a very important requirement is how you're going to install this, what it is going to be physically. And so we'll talk about the feed line or the transmission line that carries your signal from the transmitter to the antenna. And where you're going to put the antenna. Is it going to be at the top of a tower, for example? And then finally, the environment. Is it close to something else? Because if it's too close, then that can interfere with its operation. We'll talk about that. So how can we make a decent antenna, an antenna that works? Let's take a look. For this video, I made an antenna by reaching into my box and pulling out a coax that terminates in some alligator clips with some leads. And laying it on the floor in this fashion, with the leads going up and down, perpendicular to the feed line here, makes an antenna. And what kind of an antenna does it make, and what frequency does it work at? Well, let's take a look. The frequency for this is around 440 megahertz. How do I know that? There's a ruler down here, and this thing's about 30 centimeters long. So if it is, as it looks, a half-wave dipole, then that would mean that it would work at a wavelength of 60 centimeters, which is close to the 440 band. 440 megahertz band is typically mentioned to be 70 centimeters, but these antennas built like this need to be a little bit shorter than a half wavelength physically, and so I'm guessing that this thing would work quite well at 440 megahertz. If I test it with a nano VNA, for example, and it turns out that it's a little off, then I can just clip on some extra length to it, for example. Or if I want to make it work at, say, the 2-meter band, then I'll just lengthen it with some extra wires and shove them out here, make it longer. So what could be the main use for this? Well, it would certainly work on receive. And it would probably work quite well on transmit, as I've shown it here. However, as soon as I try to move it around, these leads will not be in this position anymore, and it probably will not work very well for transmit. The impedance of this antenna, as shown, is about 50 ohms. Okay, now I know that some of you may know that a half-wave dipole is 73 ohms, but this is an unbalanced half-wave dipole. As we've said in a previous video, we've measured these in the lab, and they come out pretty close to 50 ohms because of that unbalance. Directivity and gain, they're just pretty much a dipole, so it's about 2 dBi. The pattern's a little off, but who cares about a dB here or there typically. Polarization, it is linearly polarized, as opposed to something called circular polarization. This is a linear polarization. The feed line here is RG58 coax, a 50 ohm coax. The sighting, as I mentioned, it's laying on my floor upstairs, which is important because if it was laying on the floor in the basement, then what would be underneath it would be concrete and it would not work well at all. The structure is not very much. I can't pick this thing up, so this is a terrible antenna, honestly. However, I could tape it to this ruler and then put another ruler this way and tape those together and have a almost usable antenna. All right, and the environment, as I said, it's laying on the floor, so what's underneath it is carpet and wood. Does that affect it? Yes, but not a huge amount. Okay, so coming back to our 2-page class handout, that's an example of a half-wave dipole antenna. But in this video, my goal is to lay the groundwork for us to understand all of these different types of antennas and more. So we've covered kind of a half-wave dipole, and we're going to look at some monopoles, some loaded monopoles, some loop antennas, patch antennas, and so forth. Turns out that sounds like a lot, but there really are some key aspects that if we get that theory down, then we can understand all of the others. So what are the essential aspects of antennas? This slide, which I've taken from episode 5 in this series, sums up a lot of that. And we've covered this slide a few times before, so I'm not going to spend any amount of time on it, other than to point up a few key elements that we need to talk about. One is the transmission line that takes the signal from the transmitter over to what's called the feed point of the antenna. And here's our dipole antenna. So this feed line, the purpose is to simply do that transport of the energy to the antenna. We do not want it radiating. And as we'll see, the key to making sure it doesn't radiate is to make sure these wires are close enough together. Because then the current that's in the top wire will create a field, but it will be canceled by the current in the bottom wire because that current's going the other way. So we get no radiation in this direction. We get no radiation from the feed line and only from the antenna itself. So that's important take home number one. What about the antenna itself? How does that work? Again, we've discussed it before, but very quickly, if you put a voltage at the feed point, then there's some capacitance between this metal rod and this metal, and I've shown that here, and that creates an electric field in that region. It also sets up some current because even though this is very small capacitance, we're at radio frequencies, which are very high. So you can get a low enough impedance to start current flow in these rods. And the currents I've represented by the arrows. And as you know, current creates a magnetic field around it. And I did not explicitly show it, but that creates inductance in this element too. So we've got some inductance here, we've got some capacitance here. We'll see that come into play later. Now, if all goes well, then we launch the EM waves, and they get over to a receiver, and they induce some currents in the receive antenna and develop a receive voltage, which is amplified and received like we talk about in our Radio Design 101 series. So this slide shows a progression from a transmission line, which ideally does not resonate, again, if the wires are close enough together, which means much less than lambda over 2 separation typically, to a sort of dipole where I just spread these things out a little bit more. You can see they're kind of tilting out. They're not perpendicular as it is over here in the short dipole, but they are spreading out. And this thing will radiate or receive. It just won't do it as well as something like on the far right. We have an antenna which is exactly the right length, half wavelength. And that's the so-called resonant dipole. So how important is this length of lambda over 2? Well, if you've been around antennas before, you may know that that plays a strong role in the impedance seen looking into the antenna terminals. So when we hook up our transmitter voltage source to the feed point of the antenna, how much current is developed here? And from that, as we've talked about in previous videos, we could determine the far field strength that the antenna creates as it radiates. And of course, we know from episode 1 that lambda depends on the frequency. So the wavelength lambda is what? C over F, where C is the speed of light and F is frequency. And in this entire video series and others, I use SI units, so I just use meters per second for C and hertz for F. And then the result you get is in meters. Now, what happens if the antenna is not long enough, when it's not lambda over 2? Well, down in the bottom left here, I've created some schematics, both of a transmission line. Suffice it to say that we've got some inductances and capacitances for the same reasons we were talking about with the antenna. And if you hook up a voltage source on the left side here, then this whole complicated network looks like a, say, 50 ohm resistance if it's RG58 coax. And so your signal gets transferred down here, and if the other side is 50 ohms, if it matches the so-called characteristic impedance of the transmission line, then it goes on out the antenna. Now, what does the antenna look like? Well, it looks like a resistance in series with a reactance. And if it's half wavelength long, the reactance is 0, and it just looks like a resistor, which hopefully is, say, 50 ohms. So that it matches the transmission line and none of that signal gets reflected back. All right, now the key thing here having to do with the short dipole is the fact that this resistance is the radiation resistance, which is what I was just talking about, but there's some physical resistance at play too, in the wires and in the element of the antenna. And it may seem like it's small, but because of skin effect, the currents only flow on the outer micron or few, and it can be substantial. It could be an ohm or 2 at radio frequencies. So that's important because when we shorten up the antenna, the radiation resistance is no longer 75 or 50 ohms. It'll drop down to as much as 1 ohm. Depends on how short it is. At the same time, for either my sort of dipole here or my quarter wavelength dipole thing, it's no longer resonant, and so we get a reactance here. And it will be some negative J, so it will be a capacitive reactance. And it could be several tens of ohms or even 100 ohms, depending on how short the antenna is. So that's admittedly a little bit complicated, but it can be addressed by putting some loading coils in series with the antenna elements, as we'll talk about later. And that can get rid of the reactive part, but you're still left with the fact that the radiation resistance is small and the physical resistance may be comparable. So what happens in that situation is the antenna is not very efficient. You lose a lot of power in heat losses in the physical resistance, and not as much gets radiated. And that's why for a dipole, we generally prefer lambda over 2 for length. It just makes things simpler and it makes it more efficient. And that's all fine if you're operating at 440 megahertz, as I was when I did this little demo. But Marconi did not have that luxury. So the antenna that Marconi built for the transatlantic test was huge because the frequency was much lower, say 300 kilohertz or something in that range. And so the antenna was much larger. Now, Marconi's antenna was not a dipole for that transatlantic test. It was a monopole above ground. And so I've shown that on the right here. This is essential theory for monopoles. The dipole had 2 poles and it was lambda over 2 in total length. The monopole has 1 pole and it should be lambda over 4 in length. It doesn't need the other pole because of the existence of a ground below it. So this symbol right here with all the little hash marks means you're seeing the side view of ground, which in this drawing of Marconi's antenna is the Earth. This antenna, quarter wavelength monopole, has an input impedance ideally equal to half of the dipole, and the dipole was 73 ohms. Here it's 36. What happens if you make the monopole shorter than lambda over 4? Well, same thing as what happens with the dipole. It becomes a resistance, which is much less than 36, in series with a reactance, which is capacitive and large. How do we deal with that? Put some inductance in series with the element in order to make it purely resistive. And it's interesting that you can actually, with a single coil, you can make these things have an impedance close to 50 ohms. So short monopoles are very popular. Can't make them too short. You can get down to say lambda over 8 and still have them pretty efficient, or even lambda over 10 or lambda over 20, but not much shorter than that. Finally, in our overview of essential theory of antennas, I should mention that it's possible to create what are called loop antennas. Let's take the resonant loop on the right-hand side. Each side is lambda over 4, so that means the entire circumference is 1 wavelength. When you do that, because it's resonant, there's no reactive term to the impedance of the antenna, and you just have a physical resistance in series with the radiation resistance. And the radiation resistance is somewhere around 120, 150 ohms. It depends a lot on what's nearby. Of course, it's possible to create small loops, but when you do that, the radiation resistance goes down, of course, but the reactance goes positive because you're creating a little inductor. And you can counter that inductive reactance with a capacitor. And again, in part 2 of this video, we will cover some real-world examples of antennas, including some of these loop antennas. Something like I've shown here is used in the key fob that opens your car, most likely. I'll show you the internals of a key fob. And this loop is something you may find in an AM radio receiver or one of these 60 kilohertz atomic clocks that resets itself every midnight to the exact precise time, transmitted from Fort Collins, Colorado, in the US at least. So you can kind of see that we're starting to fill out the theory for all of these antennas. All the other antennas that you see here are handled with the same theory. These Yagis and log periodics are just multiple dipoles that use phasing to get a good directivity and gain. Same thing here for the linear vertical array. These could be half wavelength dipoles set up in a vertical array to get a particular pattern and gain, as we've seen in some of the previous videos in this series. And similar things can be used at the feed point for a parabola to get high gain and very directive antennas. So we're covering the theory which is needed to understand all of these. But there is one more or a few more key points that are needed to understand how to transition from that theory to real-world examples. So we'll spend a few minutes on this slide. This slide is a little dense, but that's because I'm trying to pack a lot of information into a reasonably short time, as we've done throughout this series. Let's start with the picture in the lower left. This is what was on our title slide. And there's a radio here with a black antenna going up. And this black antenna is a loaded monopole. It's got some inductance in it here, probably at the base, and then a rod up here. It's covered in plastic. But here's the thing. Where is the ground plane? If this is a monopole, loaded monopole antenna, where's the ground plane? Or maybe this is not a monopole. Maybe this is a dipole, but where's the other half? Well, it won't fit completely into here. But inside here, there is a circuit board, there is a ground plane, and that's where the other part of the antenna is. It is neither a dipole nor a monopole above a ground. It's a sort of dipole. So I've drawn a representation of that on the right, and I called it monopole slash dipole with a regular counterpoise. So this is the metal in the circuit board. The shape doesn't matter. Even the size doesn't matter, provided whatever size is here is compensated with a little change in the main antenna rod up here. And this metal down here, whatever shape it is, in this case it's a circuit board, ground plane, is called the counterpoise. And it basically serves the purpose of the other element of a dipole, for example. So this would be the antenna that you actually see and think about, but the rest of the antenna is inside the radio, that ground plane. And the feed point is right here. Now, the rest of it is the same as before. There's a transmission line, which could be coax, could be twin lead, or in the case of this radio, the circuit board probably comes right up to the feed point of the antenna, and there probably is no transmission line to speak of. If this antenna is not the right impedance, whatever that is, we could modify that with what's called a matching network. And in that case, the matching network can incorporate something to counter the reactive term and then take the resistive term, whatever it is, and convert it to what you want, like the proverbial 50 ohms. And that resistive term, as you shorten the antenna up, it decreases as the square of the length for short dipoles, or as the square of the length for short monopoles. Let's take the dipole case. As we know, an ideal half-wave dipole, a resonant dipole, has an impedance of 73 plus J0 ohms, purely resistive and ideally 73. That's if it's lambda over 2 in length. What happens if we shorten it up to, say, lambda over 4? Well, it becomes a short dipole. It's less than lambda over 2. In fact, it's 1/2 that length. So the length is dropped by a factor of 2, and this bullet says that the radiation resistance is going to decrease by a factor of 4, from the ideal 73 to about 18. As another example, let's say we went from lambda over 2 down to lambda over 20 in length. You might need to do that if you're operating at a very low frequency, not in the hundreds of megahertz, but rather in the tens of megahertz. Well, in that case, we're dropping the length by a factor of 10, so the radiation resistance will fall by a factor of 100, from 73 to 0.73 ohms. So this term right here is 0.73 ohms. Meanwhile, this reactive term is probably something like minus J100. Well, both things can be fixed and converted to 73 or 50 or whatever you want with a matching network. However, you've got this physical resistance that's involved as well. And when the radiation resistance drops to 0.73, it's probably less than the physical resistance. So most of the power that you're trying to radiate with your short dipole then is going to be absorbed in that physical resistance or in resistances in the matching network elements. So what does that mean? That means that efficient antennas generally need to be greater than lambda over 10 in size. lambda over 100 is probably not going to work very well. But as the third bullet says, there is no magic number, especially for receive operations. So lambda over 100 length antenna can work for receive. Why is that? That's because receivers usually have a very high dynamic range, and you often have signals that are much stronger than you need. So even if the antenna is really crummy, it'll still work. And we talked about that a little bit in the Radio Design 101 series in the epilogues, where we found out that in some cases a shorter antenna is actually good because it allowed us to not get overloaded with super strong signals, say in the FM broadcast band. But for transmitters, you do need to adhere to these sorts of rules. Finally, watch out for nearby objects. In the last video in this series, we showed what happens when you take a dipole and you stick it next to a metal door, for example. It just doesn't radiate at all. And if we had looked at the input impedance, we would have found that it was totally destroyed. So you got to watch out for any objects, especially ones that are closer than lambda over 2 to your antenna, because they can have strong effects on the impedance and the operation of the antenna. So these are the key points that I wanted to mention about transitioning from the ideal stuff that everybody talks about to real-world antennas. Before we leave this slide, let's take a quick look at this other antenna that's shown in it. This is the FM broadcast radio that we designed and built in Radio Design 101 video series. There is a ground plane on the back side of these circuit boards, and there's a coax going from the receiver input to the antenna. And the antenna is this, or is it? All right. Other key point to remember. There's always a counterpoise. This is an antenna element. This is what our brain says is the antenna, but this is not the antenna solely. The antenna consists of this rod as well as the counterpoise. Where's the counterpoise here? Well, the counterpoise is wherever the electric fields in this rod want to terminate. And the feed point is right here where the coax attaches to this. The center lead goes into this rod. The shield just ends here. So the other side of the antenna is the shield and the shield of the coax, and then the circuit board ground plane here. So this is an example of a very irregular counterpoise. It's not shaped like this at all. It's just a linear shield here. It almost looks like a dipole. In a sense, you could consider it kind of a dipole, but the pattern's going to be kind of messed up. And the ground plane is at play, so that changes things too. So always remember that, and remember that nearby objects can also have strong effects. So there's metal in this radio, which is probably having some effect. But the thing can still work. Now, the topic of this video is designing antennas, and I hope we've shown how to do that. But I would be remiss if I didn't point out how to not make antennas. And that's what I'm going to talk about for the next few minutes. And then in part 2 of this episode, we will cover these last two topics here. This subject of how to not make antennas is very important in product design, especially if you're going to market that product. If you are not careful, your product can create what's called radio frequency interference and cause big problems, as we'll see. The governing bodies generally refer to these situations as unintended transmitters. But here we're talking about antennas, so let's talk about the antennas that create that transmission of radio frequency interference. Where are those antennas? Well, this is an Arduino board, and there are a bunch of wires here, and I'll bet those are antennas. This is a little proto board, and there's a ground wire that goes from this hole over to the ground strip here, and this is a bad idea because look at that, that's a loop antenna for any sufficiently high frequency. At audio, you don't care about this stuff. Generally speaking, you can build stuff with proto boards. However, at high frequencies, you could have RF currents going through this and radiate. And where do the RF currents come from? This is a FPGA board, kind of like an Arduino, and there are digital waveforms with very sharp edges that have harmonics that go out into the gigahertz region. Another common place to have these sorts of problems is in motors and motor controllers. In modern motors that are three-phase, you have inverters, and those will switch at something like 40 kilohertz, but the edge speeds are so high that it can generate interference out into the hundreds of megahertz and beyond. Whereas the antennas, well, we've twisted the wires here to try to keep them close and not radiate, but when you hook this up to a power supply, for example, then you've got a loop here, and at sufficiently high frequencies, this will become a decent loop antenna and radiate, similar to the wires that go to the actual motor itself and these wires that go to the control. Now, if you're skeptical and you think this is all a bunch of hoopla, it's not. This is the inside of a building that we moved into recently. A beautiful new engineering building built to high energy efficiency standards. And so that means there are fluorescent lights with switch mode power supplies in them to get very high efficiency. And there may be some LED lights in this building as well. And before we actually moved in, I hauled a spectrum analyzer into the completed building with the lights on, and I hooked it up with an antenna, just a 20-inch rod or so, and swept from 0 hertz to 1 gigahertz to look and see what the spectrum looked like. What I should have seen is a few bunchings of sharp vertical lines above the noise floor, which would be this blue line. What I saw instead is this mess. This is in-building radio frequency interference. And it is 40-50 dB above the analyzer noise floor and as much as 60 or 70 dB above the theoretical thermal minimum noise floor. So that means if I'm trying to receive a signal that is weaker than wherever this yellow line is vertically here, some signal closer to the noise floor, I'm not going to get it. And in fact, I could only receive 2 FM radio stations inside this building, even though outside the building I could get 24 stations. So this investigation was written up in a paper called Wireless Communication Problems in Energy Efficient Building Construction and published in the 2016 International Symposium on Electromagnetic Compatibility, or EMC. They're the body that deals with this issue, along with governing bodies that control radio frequency emissions, like the FCC in the United States. The FCC had rules that said that these ballasts had to be checked and make sure they don't have conducted emissions out the lines that power them up through 30 megahertz. Unfortunately, the switch mode power supplies here produce edge speeds that throw harmonics out into the hundreds of megahertz range, as you can see here. So it passed the rules, but it didn't work in the building because as soon as this was hooked up to the wiring in the ceiling here and in the walls, all that wiring became a huge antenna and just flooded the building with RFI. I also checked household LED bulbs, and very briefly, this is a ferrite choke that people sometimes put on wire lines to stop the interference. My experience with these is they don't work very well above 100 megahertz or so. I was using this to actually sense the amount of signal that was going out this power line on this little lamp, and you can see the spectrum there. So it's pretty much the same deal as with the high efficiency fluorescent lights, except that people have these in their homes. So LED bulbs, as well as lots of products in your house. Anything with fast rise time waveforms and inadequate bypass and filtering on the power supplies and or shielding. Most computers have a metal case that prevents them from doing much of this, but a lot of products will generate radio frequency interference. How to avoid that? You need to pay attention to 2 things. One is the source of that interference. In this case, it's a switch mode power supply, quote, ballast for these lights. And also, what are the antennas? What's the wiring that is emitting the signal? If you want to prevent the radio frequency interference from happening, then here are a few ideas. Number 1, provide good power supply bypass and filtering. So on a circuit board, there may be power coming into a component, and you need to put a bypass capacitor very close to that component. And here it is in the schematic form. It just goes from the power supply line to ground. And on the back side of this board is a ground plane. That's the other key element, is to have ground planes in your circuit board designs. And because any loops, such as this wire here, will form antennas, you need to keep the components close to that ground plane and preferably use small components, surface mount technology components, such as the little chip capacitors and resistors in this guy. Use twisted pair wiring, such as shown here, or in general what I'm going to call ground paired wiring. For example, in parallel buses in a computer, there will usually be grounds paired immediately with each signal line. And sometimes you actually shield the wiring. Finally, test the product and/or the full system for electromagnetic compatibility, EMC compliance. There are rules that you have to follow, especially if you're going to market, sell a product. And if you have to, encase the product in a shielded enclosure like a typical computer. So that's it for part 1 of this video. In part 2, we're going to survey common antenna designs, like the ones we showed in the class handout. But we're going to do it with some nice photographs and talk through the performance of the different antennas, such as these. And we have the background now for doing that. As it says here, note that many commercial designs are variations or combinations of these basic antenna types that we've talked about today. So I hope this has provided a good grounding for us to do that in part 2. And I hope this material has been useful to you in its own right.